Welcome to ASU's University Academic Success Programs. This video will cover the topic, Valence Electrons and Lewis Structures.
I don't think I understand what valence electrons are.
Valence electrons are electrons that occupy the outermost, highest energy electron shell of an atom. These are the electrons that participate in chemical bonding. Let's take a look at the periodic table. The groups, or vertical columns, give us an idea of how many valence electrons an atom of a certain element will have. Groups 3 through 12 are the transition metals, and they have unique properties, so they're excluded from this trend. When discussing valence, one important concept is the Octet Rule.
I think I've heard of that. Doesn't it have something to do with 8 electrons?
You're on the right track. The Octet Rule is a general rule that helps us understand bonding. This rule suggests that for main group elements, the valence shell is full when there are 8 electrons in it. Let's take a look at the noble gases. Almost all of these elements, except helium, have the characteristic of carrying 8 valence electrons. These elements are known for being chemically inert, or highly unreactive, because their valence shells are already full. When atoms of other main group elements participate in bonding, they aim to have 8 electrons, as this would fill their valence shells. Electrons in a bond are lower in energy than non-bonded electrons, and filling the octet lowers the overall energy of the atoms involved and consequently increases stability. Just like in many other aspects of chemistry, there are exceptions to this rule. For example, the first shell closest to the nucleus can only hold 2 electrons rather than 8. So a hydrogen atom, whose single electron occupies this shell, only needs 1 additional electron to result in a full valence shell of 2 electrons.
Okay, so how do valence electrons and the octet rule relate to Lewis structures?
The Lewis structure model helps us understand covalent bonding in which electrons are shared between atoms. Let's take a look at hydrogen. We represent the atom using its chemical symbol. Neutral hydrogen has 1 valence electron, and we represent this by drawing 1 dot on the side of the chemical symbol. Now, what would happen if a second hydrogen atom came around, and these 2 atoms formed a bond? The 2 atoms will share their electrons, and we can represent this by erasing the dots and now drawing a line between the 2 atoms, which represents a covalent bond. Now each atom sees the 2 electrons in the bond, and the valence shells of both hydrogen atoms are filled.
What if the atoms had more than 1 valence electron, like an oxygen atom bonding with another oxygen atom?
An oxygen atom has 6 valence electrons. If we want to make O2, we need 2 oxygen atoms that want to make a molecule. Each atom wants 2 electrons to achieve an octet and fill their valence shells. These oxygen atoms each have 2 electrons to share, and there will be a total of 4 electrons shared between the 2 atoms. Here we see that the oxygen atoms have formed a double bond. Now let's take a look at ozone, whose chemical formula is O3. One possible Lewis structure would look like this, but it's missing something. Can you tell what's different about this structure?
Well, I know that neutral oxygen has 6 valence electrons, and the one on the right is drawn with 6 electrons in pairs and 1 in a bond, making 7. This means that the oxygen on the right has a negative charge, right?
That's exactly right. And the oxygen in the middle is drawn with 2 electrons in a pair and 3 in bonds, making only 5, so this oxygen will have a positive charge. But we didn't have to draw the Lewis structure this way. We could have also drawn the oxygen on the left as the negatively charged one.
So, which structure is correct?
Technically neither. Both of these structures are what we refer to as resonance contributors. In reality, the negative charge is equally distributed on both the left and right oxygen atom. When electrons are delocalized and cannot be expressed by a single Lewis structure, we can draw a resonance hybrid. The resonance hybrid takes the contributing structures into account and is a more accurate representation of the real structure. To draw the resonance hybrid, we first need to identify the pieces of the contributors that remain constant. In both resonance contributors, the central oxygen has a lone pair of electrons and at least one bond to each terminal oxygen. And each terminal oxygen has at least two lone pairs of electrons. So what changes between the structures is where the double bond is located and where the additional lone pair of electrons is located. We can draw dashed lines between the atoms to account for this. Also, since the negative charge is distributed equally on the terminal oxygen atoms, we can say that each one has a charge of -1/2. To complete our depiction, we can draw resonance arrows between the contributors and brackets around them.
Okay, so when drawing Lewis structures, we use a chemical symbol to represent the atom, and dots to represent the electrons. We only draw the valence electrons, which are the electrons in the highest energy shell of the atom. Atoms typically aim to fill an octet, with some exceptions, and can achieve this through chemical bonding. In a Lewis structure, we represent a bond as a line between two chemical symbols. If an atom within a molecule has a charge, we identify it, and if a molecule can't be represented by a single Lewis structure, we can draw resonance contributors to construct a more accurate resonance hybrid.
That's exactly right. Great work!